Union has named a small asteroid after him. So please join me in welcoming Martin Harwit to deliver his lecture, In Search of the True Universe, the Tools, Shaping, and Cost of Cosmological Thought. Professor Harwit.
When we look up at the sky at night, we see an abundance of stars, some far brighter than our own star, the Sun, others considerably fainter. Many may be orbited by planets, comets, and asteroids similar to those in our own solar system. In this slide, a long exposure of our nearby surroundings obtained with the Hubble Space Telescope, the blue streak that you see up the upper right was traced by a small asteroid, sort of ambling along, pursuing its orbit around the Sun, but just getting into the exposed frame here. Our Sun and all the other stars that I show here are part of the spiral of the Milky Way, a spiral galaxy consisting of 100 billion stars. If we were able to view the Milky Way from afar, it would look very much like this. The Sun would be about halfway out to the rim of our galaxies. Let's see how this works. Sun would be about halfway out to the rim of the galaxy. This one here is called NGC 1032, but it's almost identical to the galaxy that we are in. Most galaxies are members of a cluster that might contain just a few galaxies or several thousand bound by mutual gravitational attraction. This attraction is so strong that it bends the trajectories of light much as a camera lens would. The forces give rise to the faint circular streaks that you may be able to see on the right side, upper right side of this cluster here, and then also you see some of these circular streaks. Those are caused by the bending of light by gravitational forces. But galaxy clusters, in turn, are part of a much larger cosmic web that extends as far out in space as our most powerful telescopes can reach. The dark, bow-tied-shaped spaces on the right and left in this slide are due to the clouds of gas and dust in our own galaxy, the Milky Way, which block our view of those portions of the web which nevertheless pervade the entire universe. The study of planets, stars, and galaxies constitutes the everyday work of astronomers. The findings of their studies may be arrayed into some mental landscape of the universe and its working that most astrophysicists carry around in their minds, and which I sketch here as a cartoon. Although no two astronomers are likely to see this landscape in totally identical ways, it represents a shared view of the universe. It mirrors the interaction of stars with their surroundings, the interplay of galaxies with their clusters, and our heritage from an earlier phase in the evolution of the universe in which some of the chemical elements we see around us today first were forged at temperatures of order of billions of degrees. The everyday task of the astrophysicist is to gather additional information and make sure the new pieces of observational and theoretical evidence fit neatly into this landscape, making sure nothing is missing and, to the extent possible, everything is tidy and explained. This can be an arduous process. Each newly gathered piece of evidence clamors for a place in the landscape but often will not fit. To accommodate it, neighboring parts have to be moved around, and so the landscape continually changes. But although the astrophysicists often think it is, this landscape is not totally isolated. Occasionally, some other form of human activity intrudes, drastically altering the landscape. Astrophysics is then in temporary disarray, unrecognizably disfigured. The landscape then needs urgent reconstructions. But what are these other activities? Well, in the example shown here, it was the development of entirely new and powerful gamma ray techniques developed by the military for its own purposes that unexpectedly intruded on astronomy and revealed the existence of a most mysterious set of bursts of gamma rays, a variety of energetic X-rays. What were these gamma ray bursts and how had they come about? In the mid-1960s, the United States and the Soviet Union were engaged in a Cold War, a scramble to gain military ascendancy. Perhaps the most phenomenal astronomical discovery this brought about, the discovery of gamma ray bursts, came in 1968. So secret was the finding that it remained classified until 1973. So why the secrecy? Well, the Atmospheric Test Ban Treaty, signed in October 1963 by Kennedy and Khrushchev, had finally banned the testing of nuclear bombs above ground so as to eliminate radioactive fallout that they created. The problem the treaty posed was that an antagonist could then learn a great deal about the yield of a weapon tested underground, where testing was still permitted, by sensing the seismic waves that it produced. The United States worried that the Soviet Union might strive to seek greater secrecy by exploding its test devices not underground, but surreptitiously at great distances out in space. To detect such bursts, the United States designed the so-called VELA project. It involved several gamma-ray sensing satellites in Earth orbit, stationed so at least one satellite would always be positioned to detect nuclear explosions anywhere in space. The first gamma-ray burst the VELA satellite detected must have been a tremendous shock to the military. And then others followed every few months. Very short bursts, sometimes lasting only a few seconds or less. Once the military realized that these bursts were not due to Soviet nuclear bombs, but to unimaginably vaster explosions somewhere out in space, they declassified them and published their findings in the astrophysical journal Letters. The news stunned the astronomical community. It then took another 25 years for astrophysicists to find that these bursts originate at extreme distances in the universe, and their power is staggering. In the post-World War II era, radio, X-ray, gamma-ray, and infrared observations and their discoveries shook up the field in such ways, time after time reconfiguring the landscape. Often we didn't even have time to pick up the pieces and reassemble them before the next discovery disrupted our efforts. Each major discovery came as a surprise because the landscape that had previously been assembled had meticulously attempted to exhibit continuity and scientific coherence, leaving little room for unexpected external influences. Until World War II, our astrophysical theories had been too narrowly defined by observations gathered almost exclusively at visible wavelengths. The Cold War introduced new technologies led to the discovery of phenomena which had left no imprint of themselves in visible light. Viewed in isolation, these technologies, shown at the bottom in the technological landscape, constituted a totally different, previously largely ignored world, a landscape of their own from which time and again disturbances emanated to alter the astrophysical landscape. The tools these technologies could provide had, and even today have, no assigned place in the astrophysical landscape. That is, our views about the world that we live in. But if you're cognizant of the technological landscape, you possess information about the conceivable ways in which the cosmos might ultimately be studied, and have a map in your mind which tells you where observational astronomy has thus far failed to take a foothold. This is where new observations will most likely produce novel insights. The universe is so complex that theoretical predictions have usually failed to extrapolate from known observations into areas where observations are still lacking. Now you may ask how this influx of military tools first had hit astronomy, and why just as the Cold War was setting in. To answer this, we need to turn even further back in time to 1945 and the war's approaching end. Vannevar Bush, born in Everett, Massachusetts in 1890, obtained a doctorate in engineering jointly from MIT and Harvard in 1916. By 1919, he had joined the faculty of MIT, where one of his greatest successes was the construction of a differential analyzer, a machine designed to solve differential equations. In 1932, he was named Dean of Engineering and helped transform MIT into an institution dedicated not only to advanced engineering, but also to research in the basic sciences. Bush saw more clearly, perhaps, than anyone else in the United States how linkage between abstract science and practical engineering could solve complex problems facing the nation. A call in 1938 to head the Carnegie Institution of Washington, one of the largest foundations then supporting American science. You have to know that the federal government supposedly supported hardly any science in those days, in pre-war days. This call from the Carnegie Institution brought Bush to the nation's capital. Once here, he requested a meeting with President Franklin Delano Roosevelt. In this session with the president, which lasted only 15 minutes, Bush handed Roosevelt a memorandum proposing a novel blueprint for scientific research. It argued that the nation's universities were better equipped than any other institution to offer powerful scientific leadership in the looming prospects for war perceptible by then. Roosevelt wasted no time in approving the document with a scrawled, "OK, FDR." That was it. Bush was appointed head of a newly created Office of Scientific Research and Development, OSRD, tasked with shaping military research strategy on an equal footing with the Army and the Navy. As head of OSRD, Bush oversaw a wide range of World War II developments as diverse as advancing radar, accelerating the Manhattan Project to build an atomic bomb, and rapidly producing the new medical miracle, penicillin, for wartime use. As the war approached an end in late November 1944, Bush turned to planning the future. Once again, he sought the president's support. In response, Roosevelt formulated a letter which Bush had helped him to craft. The letter began with the words, "The Office of Scientific Research and Development, of which you are the director, represents a unique experiment of teamwork and cooperation in coordinating scientific research and in applying existing scientific knowledge to the solution of technical problems in the war. Its tangible results can be found in the communiques coming in from the battlefronts all over the war. The information, the techniques, and the research experience developed should be used in the days of peace ahead for the improvement of the national health, the creation of new enterprises bringing new jobs, and the betterment of the national standard of living. It is with that objective in mind that I would like to have your recommendations." In response to the President's directive, Bush submitted a report on July 5, 1945, on which some of the finest technical, scientific, and legal minds in the United States had worked over the winter and spring. Its title was Science, the Endless Frontier. The report had been completed in only 7 months, but by then Roosevelt had died, and Bush submitted the document to President Truman instead. The summary of the report was a visionary statement, largely crafted by Bush himself. Bush saw science as a key element in a seamless effort to improve the welfare and security of the nation. Training young scientists would play a leading role. The effort would require oversight by a new agency which would recognize that freedom of inquiry must be preserved and should leave internal control of policy, personnel, and the method and scope of research to the institution in which it was carried on. 5 years elapsed before Congress passed a bill in March 1950 establishing the National Science Foundation as the institution Bush had envisioned to carry out his recommendations. Not everything Bush had requested was granted, but most of his major recommendations came through unscathed. Predictably perhaps, the US astronomical leadership was decidedly unenthusiastic. Powerful observatory directors like Otto Struve at the University of Chicago's Yerkes Observatory and Harlow Shapley at Harvard foresaw correctly that governmental funding would weaken their authority as directors to the point where they would no longer control the course of research. Shapley worried that governmental support would guide astronomical research in ill-conceived directions. His vision for post-war astronomy was the continuation of the optical program the war had interrupted. Instead, the post-war years introduced new instruments originally developed for military purposes, which unveiled a universe incredibly more varied and richly textured than he or any other astronomer could have imagined. Younger scientists, however, saw a new freedom to conduct research on their own and welcomed the governmentally inspired opportunities. In the 5 years it had taken Congress to establish the National Science Foundation, the nascent Cold War had focused research and development on national security. In 1949 to 50, the federal research and development budget was approximately $1 billion, 90% of which was shared between the Department of Defense and the Atomic Energy Commission, largely concerned with nuclear weaponry. Through the Office of Naval Research, the military also was the main supporter of basic science research in academic institutions. By 1953 and the Korean War, military research and development was funded at a level of $3.1 billion and increased by a factor of 3 in just 3 years. The launch of Sputnik, the Soviet satellite Sputnik in 1957, shocked the United States into investing even more heavily in research. Under President Dwight D. Eisenhower, NASA was established to conduct a civil space program separate from military space efforts. The National Science Foundation budget also grew. By 1967, the federal research and development budget had grown to $15 billion, another factor of 5. You can see that in the top curve on the left. It's slightly faint because this is a 1977 document that I copied it out of. You can see that the actual dollars, the value of the actual dollars, leveled off around 1967 because of inflation, but otherwise, in terms of actual money that was printed, you can see the steep curve here, which increased the total research budget by about a factor of 5 in just these few years. So by 1967, the federal research and development budget was $15 billion. Another factor of 5, as I said. But only half of that was related to defense. The National Science Foundation budget that year approached to $500 million, enabling the foundation to provide more than 13% of the federal support for academic research. The Departments of Defense, NASA, and the Atomic Energy Commission jointly provided another 34. So out of the total $15 billion, about $5 billion by the end of that decade, or by the end of 1967 actually, had been spent on basic research. US universities awarded nearly 13,000 doctoral degrees in 1967, more than twice the number awarded in 1960. 1957 had seen only 168 graduate students in astronomy in 28 US universities. 9 years later, there were 793, almost a five-fold increase. The annual growth rate of 19% in astronomy was twice the growth rate in related sciences. Totally transformed astronomy in the United States. In Britain, the pioneering radio astronomer Sir Bernard Lovell noted similar developments. So you can see this interaction of the Cold War and the race with the Soviet Union having an enormous impact on the budgets that were spent on basic research in the United States. Throughout the war and the post-war era, the military's capabilities in surveillance increased, and as the armed forces outgrew a technique, a capability, or a device, and no longer needed it, the military establishment passed it on to colleagues in astronomy who often found it to reveal something curiously unexpected. So not only did we get the money that was awarded to us for military reasons, we also inherited a lot of the equipment that the military had outgrown. Time and again, unanticipated findings initiated new lines of inquiry, channeling the attention of astronomers into previously unimagined directions. Between the end of World War II and the early 1970s, radio techniques, X-ray, gamma ray, and infrared devices were leading to discovery of entirely new astronomical phenomena, stars and even entire galaxies that emitted more powerfully at radio or X-ray frequencies than at all other wavelengths combined, or dusty star-forming regions that shone mainly in the infrared. A new sense of excitement and purpose swept over the field. Here I'll mention only 3 of the discoveries of those days, mainly because their names are now anchored so closely to our everyday vocabularies. First off, quasars, discovered in 1962. These are by now understood to be rapidly rotating black holes as massive as 1 billion suns and lodged in the nuclei of galaxies. They can be more luminous at radio and X-ray wavelength than all the light the galaxy stars emit, and they often eject highly energetic jets of subatomic particles that may stretch hundreds of thousands of light years into their surroundings. And so here on the upper left, you see one of these jets protruding from the quasar like Centaurus A, which is a supermassive black hole in the nucleus of that particular galaxy. The second of these discoveries followed in 1965 of what is now called the Big Bang, evidence that the universe once was far more compact than today and intensely hot with temperatures exceeding billions of degrees. By now the temperature has cooled to about 2.7 degrees above absolute zero, but we can still see fine ripples, shown in different colors in this slide, of primordial structure dating back to the birth of time. These are essentially frozen into the fabric of space because the universe is expanding so quickly that nothing can really change if it's localized in some part at one time. Now the temperature variations that I show here go from minus 200 microdegrees Kelvin, microdegrees, up to plus 200 microdegrees and they are centered on a temperature of 2.725 degrees. So these are sort of parts in 100,000 variations that you see, but they're reproducible and they're clearly there, and they show the structure that was there at the beginning of time. And the third of the discoveries of that time that was remarkable was that of pulsars. In 1968, these are rapidly rotating, highly magnetized stars that emit regular pulses of radio waves, and sometimes, as in this slide, even visible light, as shown in the top trace of this view. If you look carefully, just below one of the steadily shining stars in the middle, you'll see that occasionally there is a spike here, and also over on where I have the green dot, and those are where the radio emission also spikes. And the whole length of time for a whole cycle, this is a typical cycle. Actually, it isn't a single cycle, it's an integration over many, many thousands of cycles that bring out what these pulses actually are. You can't see a single one by itself. But the whole cycle lasts only a little more than 20 milliseconds. So you see about 40 of these every second, faster than the eye could follow them. In other pulsars, the time between pulses can be even shorter. Obtaining the clearest view of the sky often requires launching telescopes into space to avoid the limitations imposed by the atmosphere. Here also the military paved the way in the post-war years by building a powerful armada of rockets with the help of Wernher von Braun and his army of German technical experts who had previously pioneered the constructions of rockets for Hitler, but had then been brought to the United States. Early post-war rocket testing also included astronomical X-ray payloads developed by Herbert Friedman's group at the Naval Research Laboratory in Washington. Some of you in the audience may still remember a very fine gentleman who unfortunately passed away a few years ago. X-ray emissions from astronomical sources could only be observed by launching telescopes into space, which is what Friedman's group did, because the Earth's atmosphere absorbs X-rays so strongly that they cannot be observed even from high mountaintops. This also is the reason that infrared telescopes are launched into space. Infrared radiation emanating from deep within dust-shrouded regions of the Milky Way reveal the formation of stars today within some of the coldest, most dense clouds of gas and dust. These clouds gradually contract through their own gravitational attraction that they exert on themselves until stars form in their cores, light up, and blow away with light pressure and gas emissions the natal cocoon of dust that surrounds them to emerge full-blown as new stars. Astronomical observers were not alone in benefiting from the collaboration with the military. Many leading theorists, both in the United States and the Soviet Union, had been involved in the development of nuclear bombs whose physics is closely linked to that of supernova explosions. They now applied their expertise to understand novae and supernovae. During the decades following World War II, the integration of military and scientific priorities became aligned to such an extent, and military influences came to pervade astronomy so strongly, that astronomers themselves no longer even noticed. Most of us argued vigorously that nothing in our work depended on military influences, whereas almost everything we did was dependent in one way or another on military contributions. Half a century had to pass under the post-war arrangements Bush had advocated before the extent of military influences became painfully clear, both in the US and abroad. Then, as international collaborations increased because the cost of many large space projects could no longer be borne by any one nation alone, a previously unremarked set of US export regulations that had been around since the late 1970s, the International Traffic in Arms Regulation, ITAR, of the Department of State, began to surface. These regulations proscribed the import and export, that is, the potential sharing of large classes of defense-related information, devices, computer programs, and services identified on the United States munitions list. Suddenly, the ITAR regulations were found to prohibit what had appeared to be the most innocent, mutually beneficial scientific collaborations. Most astronomers had not even been aware of the regulations' existence because sizable international collaborations only became common in the late 1980s and 1990s. Only then did US astronomers begin to realize the extent to which they had become dependent on military support in the form of sensitive detectors and other hardware and software. Only then did it become apparent that the extent to which Bush had advocated the melding of military and civil research had a downside that would need to be reviewed and revised in the context of international priorities. Three questions now arise. First, how can international collaborations in space, which save each partnering nation a great deal of money, survive into the 21st century under the present system of national priorities? A second, perhaps more important, but seldom discussed question raised by military support is the extent to which our understanding of the universe may be influenced by the tools we use. Most astronomers will argue that these tools do not influence how our community now portrays the origin, structure, and evolution of the universe. Not a bit of it. Yet, if you ask any of us what he does, or she does, he or she will tell you that he's an X-ray radio or infrared astronomer, which tells us something about the origins of their tools. Something must be awry. How can we trust what we learn about the universe when it so crucially depends on the tools we were offered by military or industry flush with money? Does a cosmology and understanding of the universe exist that does not depend on how scientists are funded, have access to tools, and develop a theoretical framework that encapsulates their findings? It's hardly conceivable that our understanding of the universe is not driven by the tools we employ. We know this because we were there once before. In the years leading up to World War II, astronomy was driven by just one set of tools, those of optical astronomy. Astronomers of the time, like Sir James Jeans, who wrote popular books, but was an excellent astrophysicist himself, pictured the universe as expanding immutably and serene. Views that dramatically differ from those we hold today, given our current knowledge of the vast explosions in gamma-ray bursts, powerful jets streaming out of the nuclei of galaxies, drastic implosions producing neutron stars. Yet, what we understand now comes from piecing together the observational results delivered by just some other set of tools, newer tools perhaps, not quite as limiting as their pre-war counterparts, but nearly so. To be sure, we know much more today than just before the onset of World War II. Nonetheless, we should remain deeply aware that only about 4% of the current energy content of the universe comprises atomic and subatomic particles and electromagnetic radiation, and that these particles and radiation components are all we are able to directly observe today. The other 96% of the energy is dominated by mysterious dark matter and an equally mysterious dark energy, about neither of which we know anything except for the gravitational influences they exert. So, the dark matter dominates the masses of galaxies and determines their rotation speeds that we observe. The dark energy controls the expansion of the universe and is accelerating it. Together, they account for more than 95.5%. That's an estimate still. It could change by fractions of percentages, but we think we're fairly confident now about the total amount of energy that they exert. If we decided to pursue a search for the energy sources current technologies cannot detect, namely this 95% of everything that's out there, the road ahead may be more difficult. Without governmental or industrial support, because the prospects for practical yield of dark energy and dark matter really are indeterminate. We have no idea how they could ever be applied. Maybe they never will. We may need to turn to private support for foundationally driven research, by which, for want of a better word, I mean research directed at fundamental questions we ask about the universe, questions that may have been asked throughout history, regardless of prospects of success or application. So, what we've been doing so far in the last 50 years has really been research conducted with equipment that not only was obtained from the military, but that also fed back in useful ways to the military. So if, for example, I'm an infrared astronomer, one of the useful things that astronomers did was to pursue a survey or several surveys of the infrared sky. Back in 1970, one had no idea what that sky looked like. And yet, if you wanted to figure out how you would trace the launch of a Soviet ballistic missile, which would emit heat, both through its trajectory through the atmosphere and because of the exhaust fuels that you would be able to see, you had to first know what the map of the sky was before you'd be able to tell where the missile was. So up to now, we've been working with equipment we got from the military. They've been sitting very quietly while we do our jobs. We find things that interest us, but there also is some feedback there that could be of use to the military sometimes, to industry to other times. We use computers, we improve on them, we write software for them. And so I was talking recently to a theorist who works closely with people who do investment theory and investment in derivatives and things like that, and they evidently are pleased to hire astrophysicists because astrophysicists are good at doing software and devising small programs. Evidently theoretical physicists don't help as much because they are more focused on doing differential equations and trying to solve problems neatly, whereas astrophysicists, I think, are just sloppy enough to do well on the stock market. And sometimes you do well, sometimes you don't do quite as well. So we now are going to be, if we want to start looking at these 95% of the energy in the universe, we may be meeting some obstacles that we had not anticipated before. Funding is essential to astronomy. It's expensive, and one has to know what to do. Now, we have had support, and quite strong support, philanthropic support, on various projects. Such projects in the past, however, had differed from these foundationally driven research projects by supporting astronomical ventures whose significant promise and yield could be estimated in. Among these might be large telescopes. So, for example, in 1985, the William M. Keck Foundation provided $70 million to fund the design and constructions of the first of two Keck 10-meter aperture telescopes. 10-meter apertures is sort of like a telescope whose entrance diameter is about from the screen to the back here of the room, quite big. And it's steerable, whereas this room isn't. Eventually, the foundation donated a total of about $140 million for the realizations of this pair of telescopes. Everyone could be pretty sure that such large telescopes would advance astronomy on a number of different fronts. Such ventures differ from foundationally driven research, such as the search for other intelligent civilizations in the universe, called the Search for Extraterrestrial Intelligence, or SETI. Such ventures of extremely high interest intrinsically, but uncertain end results and also quite uncertain ways of approaching the problem. We have no ideas how to do it or how to discover another civilization that might be intelligent. Such projects have to pursue a different path to acquiring funding. And we may have to follow that same path for finding dark energy and studying them. At least studying them intrinsically. There are studies going on now, but they just sort of look at a number of traditional astronomically accessible motions in the universe that would tell us something about the gravitational attraction that these energies produce. But they don't tell you whether it's a fundamental particle that we don't know about that's forming this matter and energy, or whether this is just a property of the vacuum, and whether there are two such properties of the vacuum, one in dark matter and the other one is dark energy. We just don't know. We don't know how to attempt such observations. There are all kinds of interesting projects, for example, huge reservoirs of xenon that are deep in the mountains in Italy, looking for things that might be interacting with the xenon. But so far nothing has emerged. The SETI project, the Search for Extraterrestrial Intelligence, has demonstrated that a single large gift at a level of $30 million, with additional $20 million then raised by smaller donations, can provide a total of about $50 million for a dedicated observatory for just these types of projects. The SETI Institute's Paul Allen Array, named after the Microsoft co-founder and principal donor, Paul Allen, was constructed in this particular way. Averaged at least over good economic times, a required annual operating expense of the order of $10 million a year may additionally be obtained through smaller donations. If these figures are taken at face value, a foundationally driven billion-dollar astronomical project, a cost that's not really unusual today, will then have to be budgeted to span something like a century at an operating budget of about $10 million a year. Now, century-long projects are ventures requiring planning with far more steadfast goals, operating procedures, and maintenance of archives than we have dealt with in astronomy to date. The social structure of astronomy would have to become more monastic, its focus on generational handover of methods and of data. Particularly difficult will be the maintenance of archives in forms with which we are familiar today. And this is because technology is advancing so rapidly, largely driven by the computer industry, which only survives as long as it convinces users that newer formats are so superior to earlier versions that industry no longer sees a reason for supporting older systems. This is really extremely damaging to any long-term archival effort. It doesn't matter what it is, but the billions of dollars that we have spent on space efforts evaporate as soon as we no longer can access the data because the computer industry has changed so dramatically that although we may have changed out and rewritten the, reintroduced the data into new systems, that somewhere along the line things break down. People no longer are able to access this data efficiently. Whether archives can be maintained when subject to ever-changing computer languages and formats and still remain fully decipherable is uncertain. For example, we don't know how to read a lot of the tapes that were produced in the 1970s anymore, let alone talk about a century. Whether a project can be carried out over a century when materials that once were in use no longer are even available to replace worn-out parts, and the precise correspondence of older and replacement parts is unclear, is also questionable. Fortunately, the last decade has shown that there exists a viable economy of the commons that was first championed by the sociologist Elinor Ostrom, whose work was awarded the Nobel Prize in Economics in 2009. In large part, the economy of the commons has been enabled by the internet, which has drastically changed privately supported endeavors by shifting the emphasis from local philanthropies to globally supported ventures. Think of Wikipedia, for example, the network-based encyclopedic effort supported privately by interested users worldwide. In 2011, Wikipedia raised an annual $25 million through contributions from more than 570,000 donors who found a common need for the services Wikipedia provides and also wrote a lot of the text free of charge. So this is something that's done by people who have a driving interest in a venture and bring their expertise, and it can be obtained from anywhere on the globe because you no longer have to look in the same town where you're living for an expert on what you need. You can get it from anywhere on the internet. SETI has its share of such users as well, the search for extraterrestrial intelligence. The economics of the commons is not traditional philanthropy, nor is it simply volunteerism in a social cause. Rather, it represents the active participation of productive people intensely interested in devoting themselves to a common purpose, which they know will require communal participation because it's not a venture from which any individual or organization could make money. That's the whole point about the economy of the commons. It tackles projects that just are not feasible for a corporation to carry out because it doesn't make money. This may then be the sole available means for funding projects that governments or industry are unlikely to favor. In essence, the economy of the commons asked for any interested individuals in a global community who can pitch in to do so in our search to better understand our cosmos. The only alternative to this would be to hope against odds that novel societal needs might someday produce the new techniques required to detect currently inaccessible forms of energy or remote intelligent civilizations. It could happen, but it's hard to tell how, why, and when. Either way, whether it's through public funding, private support, or through a communally driven economy of the commons, if we want to get to understand the origin and early development of the universe, we may have to be prepared for the long haul. It'll require a level of stamina and self-control, straining astronomy's far better known human traits, our impetuosity and impatience. Thank you.
Thank you, Martin. We have time for some questions. We have 2 microphones going around. Please raise your hand, stand and state your name and whether you're a member of the society or not.
Hello, my name is Ben Kaywood, and I was just elected in today. And my question for you is, having studied physics myself, one of the topics of contention that I've always found myself into.
Can you speak into the microphone?
Oh, sorry.
Yeah.
One of the topics of contention I've always found myself into is the subject of dark matter and dark energy. And make no mistake, I'm not doubting the aggregate measurements of galaxies and astrophysical phenomena that are far off. But my question for you is that one of the personal problems I've always had in this type of debate is that no one has actually come up with a specific measurement. And by measurement, I mean, say we're talking about dark matter. So my question is, okay, fine, define me the difference between the atomic lattice structure of dark matter versus ordinary matter. And I hear crickets. Or define me how exactly dark energy varies from normal energy. It's not matter, not antimatter. It's not all these things that we know about. It's almost a fudge factor that no one's really explained. Show me dark matter and energy in a laboratory and define to me how exactly it differs on some sort of basis. And when I hear the terms dark matter and dark energy, my question is, okay, if I replace those terms with the terms pixie dust or magic, tell me how those are different. If you can't measure it, in my mind, science is about measurement. If you can't measure it and define it, then tell me how this is still science. And I was wondering what your personal opinions on the matter are.
Okay. So the question is dark matter and dark energy just a fudge factor, or is it real? And if it's real, how are you going to measure it? And the answer to that question is, we have no idea. Seriously, I mean, I'm being serious. I don't want this to sound like an offhanded remark. But we really don't know whether we are dealing with just a property of the vacuum. And in that case, there would have to be 2 different vacua, one kind that's confined to the galaxies mainly and the clusters, and another that pervades the entire universe more uniformly. And we just don't know, and that's why you find experiments in Gran Sasso, in the mountain in Italy that I just mentioned, and you find people who are trying to just do more conventional things of seeing how matter moves around in the universe, but it reminds one in some ways of what Einstein was facing early in the universe, in the 20th century, when people were talking about an ether that was supposed to pervade the whole universe and all space, and people not knowing why it was that light wasn't being dragged along by the ether through which it was passing, because it was a wave, an undulation, and so that wave would have to be anchored, they felt, in that material of the ether and would be dragged along with that. And it wasn't. And then Einstein found a way of defining what time is, something that people hadn't worried about too much. Time for him was not something that was universal at every place, and at all times it was something that depended on how you were moving. That was sort of a mind-boggling concept at the time and made relativity a very controversial topic at the time. And it may very well be that we are just not seeing things right, that there's nothing really that represents an ether there. There's no energy there, quite possibly, but it might just be that we are not looking at the problem correctly and that somebody will uncover what it is. But you're right, we'll have to measure something eventually, or come up with a theory of why there's nothing there to be measured, as there was no ether there for Einstein to measure. I hope that answers it.
I'm Carl Merrill. I'm a member of the Society. And I was concerned about your comment about storing information. So I want to just make a suggestion that there is one storage system that's been able to store information for over 4 billion years, and that's DNA.
Yeah.
So it may be that we have to develop
Very
systems
temperature sensitive, I think. Well, I mean, we could also, I mean, we still have cuneiform records also, which isn't bad, but it's not readily portable, and you can't store vast amounts. I think DNA is better, and people are talking about that sort of thing. But it's not just the information itself, it's the formats for reading it out that, and the software for handling it then, that needs to be properly coordinated and kept constant. And the problem with the archives today is that the software that we use for reading it out keeps changing dramatically all the time and getting better, perhaps, but you can't read older things anymore. And the mindset of people also isn't right. You know, if a young guy is used to a new program, which really does very well for him, like we use IDL these days, 20 years from now, people may be using entirely different concepts that are topologically different. You know, it's not just lines of computer language anymore. It might be three-dimensional topological thing. We don't know what's going to be happening then, and that really is a very expensive proposition. You know, we've spent so much. Now, one good thing is that the United States has now said that they're going to, I think the NIH, about which you would know, has said that they are going to put in $100 million for 7 years or something like that. And Department of Energy and DOD are also interested in coordinating an effort that probably over the next decade will develop software tools at a level of about $1 billion, and maybe that will help stabilize things. But at some point, I think we'll have to bite the bullet and say, well, let's keep an alphabet together as we have in normal writing that everybody has been able to decipher for a long time. We'll see.
Hello, my name is Rudy Krutar. I am a member of the Society. When you ask what will it take to get a true understanding of the universe, you make a hidden assumption. The philosopher Quine once told me, the reality is not determined by the net sum of all of our observations of it. So reality is not something that we can understand and know that that's the way it is. Mm-hmm. It is something we can make assumptions about it, test the assumptions, and find many different ways of expressing it, but not that we can tell what's happening at the quantum level. Because it is hidden. We have the uncertainty principle. We have lots of principles that say we cannot know. So how can we get a true understanding of the universe when we can't know it?
Well, Quine was a marvelous man, and his sort of grasp that language is at the root of things was a really interesting perception, and his argument, as you point out, on another hand, was that if mathematics, as Gödel had shown, is a language which is not self-understandable, it's not complete, then, as Quine said, no language can be complete in itself. So it's true that there are always going to be linguistic problems where you don't know whether you define things correctly or whether you could even explain it to some external intelligence by sending messages to them. Could you explain to them what relativity is? And in what terms that they would be able to understand? So the language problem is a central question, but I think we have to live with that. It may be ultimately one of the problems that we'll face when we get there, but at the moment there are still physical experiments, observations that we can carry out, and until we get to the impasse where language is the ultimate hurdle, then maybe we'll have to stop there. But I think we may very well be stopped much earlier than that, because while the universe has been writing history with one hand, it's been blotting it out with the other, because in the early days and the early years, the universe was highly opaque to any messages that could pass through by electromagnetic radiation. So we can't get any X-rays, we can't get any radio waves, we can't get infrared waves, optical waves from earlier than when the universe was a few 100,000 years old. So everything there is hidden. Now, that's not the only type of information, fortunately, that we have. We have chemical information, and we know, for example, that initially hydrogen formed most of the helium that we see in the universe. And because we know that, we can tell how hot the universe must have been at one time and how dense it must have been at that time. So we have chemical or nuclear information about what the history of the early universe was up to a time when the universe was a few 100 seconds old, okay, just a few minutes. Now there may be similar information that we can get through gravitational waves that are not absorbed by the dense plasma that existed in the universe until it was a few 100,000 years old. So gravitational waves, neutrinos, are also able to pass through those. Neutrinos have the problem that they only date about as far back as the chemical reactions that took place between hydrogen and helium, because the neutrinos at that time were in thermal equilibrium with electrons. They only decoupled from the electrons about that time, and so if you looked at neutrinos, you would see a sort of a smudge with little variations in it, maybe just like the visible maps we have of the Big Bang that I showed. But the neutrinos would give you some further information about the structure, density distributions at the time the universe was a few 100 seconds old. We don't know when dark matter decoupled. If we knew when dark matter decoupled, we would at least also be able to get some idea of what happened up to that point. So there are messengers that can come through, but ultimately I think the problem of observational astronomy is going to be that the universe has erased. We used to joke about professors when we were undergraduates who were writing with one hand and then wiping the board with the other. Since we don't have blackboards anymore, that joke doesn't work. But that's what the universe has done to us, and so we have to be particularly smart in trying to get around that.
Hello, my name is Jennifer Brown. I'm not a member of the Society. I was wondering if you could speak for a moment on CERN, both how it fits in this kind of funding landscape that you mentioned, and in particularly like the quest
I'm sorry,
for
I thought this lady was talking, so go ahead. Start all over again, would you?
Sorry.
I'm
My name is Jennifer Brown. I'm not yet a member of the Society. I was wondering if you could speak about CERN, both how it fits in this kind of complicated science funding landscape you mentioned, and particularly how it fits in the frontiers of astronomy, because I believe CERN's approaching some of the same problems that are now facing astronomers.
You know, I'm sorry, I
there?
really didn't understand what you said. Could you?
CERN,
Yeah.
Centre
I'm sorry?
European for Research, the European Particle Physics Society, CERN?
Oh, CERN in Switzerland.
Yeah, in Geneva.
Well, they're trying to find all kinds of particles that might perhaps be the dark matter, the so-called weak WIMPs, weak interacting massive particles. So far, they haven't found any. And that's one of the disappointments that one has in the CERN establishment. I mean, they found the Higgs particle, which people had predicted, but they had hoped that they would find new particles and that they would be able to do new physics, as it's called always. People always talk about, we want to have new physics. Well, to have new physics, you would have to find new particles that show different symmetries, maybe more massive, more energetic, have different spin qualities, different. So things beyond what we know about the leptons and the quarks, which are the fundamental particles of which all matter consists. So, yeah, it would have been fun if they had found them. And they still have a chance. I mean, they're in the process of revving up the energy at the collider now. So if another factor of 2 in the increase in the energy brings out new particles, that'll be quite interesting. But I was talking to a colleague recently who said that there are already large swaths of theoretical approaches that people had been discussing up to now that have been ruled out by the lack of new physics that you're finding there.
Let's get one last question. Go ahead.
My name is Rebecca Prather, and I was interested in your comments about SETI needing to retrieve old data. Back in the early days of computing, they had a guiding principle and was known as upward compatibility. Any new language or any new computer had to be able to handle what its predecessor did. We've drifted away from that, and maybe we better revive that.
Yeah, well, I think that sort of thing would be ideal, of course. I think the problem is that it doesn't help industry make money. And so, you know, I have a perfectly good Microsoft system, but the next version that they offer will take me several weeks to sort of feel at home in, because it'll be totally different, and yet for the purposes that I need, what I have now would work fine, but they won't be maintaining it anymore. So yes, we'll have to figure something out that would make computers more like automobiles, where for a long time we've known what each pedal does and which one to step on if you want the car to stop, right? And we don't have that in computers. Sorry.
Well, thank you very much.
Sure.
In appreciation of your lecture this evening, we have the announcement framed and signed by all the members of the General Committee for you to keep.
Who's this handsome man here?
I have no idea, but it looks like you. Thank you. Thank you very much.
Thank you very much.
It's getting a bit late, so I'll try to be brief. Marvin is going to be around, of course, during the social hour to answer more questions. I'm sure there are more questions. So a few housekeeping items before we retire to the social hour. First, if you dine with us this evening and you have not settled your account, please see our treasurer, Bill Maish, in the back. Thank you, Bill. As I mentioned at the previous meeting 2 weeks ago, we are moving fast to the 21st century. The society now no longer accepts reservations by emailing the treasurer. When you get the announcement, look for a place to click a button or click your mouse, and then automatically you're taken to a place where you can reserve and get a announcement at the same time, so you know you've reserved, everything is in place. And to simplify things even more, we plan to have some more improvements in the future, so I'll keep you abreast of the developments. As always, we appreciate your dues and contributions to the society. The society is a tax-exempt Section 501c3 organization, and your contributions are tax deductible. If you're not a member of the society and you'd like to become a member, please see our membership chair, Lloyd Mitchell. Lloyd, thank you. You can also get on the website and apply online. And of course, that gives you the opportunity to become a member, elected to become a member, or selected to become a member. Then you receive announcements of all the upcoming events, and you have the opportunity also to dine with the speaker here at the Cosmos Club before the lecture. Also like to remind everybody that only 1/3 of the contributions of the society come from membership dues. The other 2/3 come from the generosity of the members who add extra contributions as well as sponsor lectures. So if you'd like to consider that, we'd definitely appreciate it. And if you'd like to consider sponsorship of a lecture or part of a lecture, please see any of us and we can tell you how to do that. It's very straightforward. Lastly, we have revived an old tradition of the society going back 142 years ago. After the end of the social hour, around 10:30 or so, some of us, or several of us, meet at the back of the room and continue our discussion at the Fairfax Hotel across Mass Avenue. So if you'd like to join us, please do so. Our next lecture, 2321, will be held on October 4th, 2 weeks from this evening. The speaker will be Ralph Lawrence, who is a staff member at the Johns Hopkins University Applied Physics Laboratory. The title of his lecture is Sailing the Seas of Titan, Saturn's Earth-like Moon. So hope to see all of you back in 2 weeks. That's all I have for this evening. Oh, I forgot to mention, there's one more thing I'd like to mention. As I mentioned last time, there's an event on the 29th of September, Sunday. There's some flyers in the back if you'd like to attend, or it's a kids event, Silver Spring Mini Maker Fair. So it's a well-attended event. There's a lot of booths and a lot of activities. So if you'd like to pick up one of the flyers in the back, and it's free of charge, so if you'd like to attend, that'd be great. And with that, I have no any further announcements. Is there any further business of the society? If there's no further business, I'll entertain a motion for a member to adjourn. I have a second. All members in favor? The 2320th meeting of the society is adjourned to the social hour. Thank you.